Welcome to the Van der Waals Computational Materials Group at UC Santa Barbara. We use first principles computation to model structure and behavior of semiconductors and quantum materials. We are interested in a wide range of research topics, including point defects for quantum information science, loss mechanisms in light emitters, nitride semiconductors, perovskites, binary and complex oxides, solid-state storage and transport of hydrogen, and polarization of electronic materials. Computational research plays a key role in developing a fundamental understanding of the physics and chemistry of materials, improving the properties of the existing materials, and in the discovery of new materials.
I'm studying materials that can be used to engineer the next generation of fuel cells, devices that are more robust, more efficient, and more cost-effective. And to do that, I'll take a crystal structure, like the one shown here, and input it into a supercomputer, which uses quantum mechanics, the stuff of my cat's nightmares, to run simulations to understand the fundamental atomic scale properties of these materials. For instance, we can understand how atoms move in these materials, like hydrogen shown here. It's vital for fuel cells to have very good hydrogen conductivity. Hydrogen needs to be able to pass through these materials very easily. And we can understand exactly how hydrogen moves and how efficiently it moves in these materials through these simulations. We see that this material here, barium hydride, is actually a really good material as a hydrogen conductor. And we can make it even better if we treat these atoms like Legos, take out one of these green barium atoms and replace it with, say, a potassium atom. We find that that boosts conductivity by a factor of 100. The insights we gain from these simulations will be vital for making the materials we need for the hydrogen economy of the future.
LEDs represent a fundamental change in the way we think about lighting technology. Even though the bulb itself looks like an old-fashioned incandescent, the inner workings are quite different. So within this bulb is a chip. And this chip is made up of a tiny sandwich of materials, a thin semiconducting layer between two electrodes. When we put electricity over this sandwich, that thin layer emits light. Now this layer that emits enough light to light up an entire room is only about 1/1000th of a meter thick. So to put this in perspective, you could stack 1,000,000 of these layers on the head of a pin.
We also study materials for applications in quantum information science with an emphasis on quantum defects. Specifically, we use computational methods to identify and characterize novel defects that are promising for quantum computation, quantum communication, and quantum metrology. For example, we have identified dangling bonds and the carbon dimer as the defects responsible for the observed single photon emission in hexagonal boron nitride. We also are actively engaged in developing the methods necessary for a full characterization of quantum defects from first principles.
Gallium oxide is a wide bandgap semiconductor with a high breakdown field. It can be easily n-type doped. These properties make gallium oxide a promising candidate for high-power electronic devices. To fully exploit the potential of gallium oxide, high-quality epitaxial growth is required. I'm interested in studying surfaces of monoclinic gallium oxide and explore the role of at-atom adsorption and diffusion on the epitaxial growth of the material. The Van der Waals group started working on gallium oxide before the year 2010. Our early paper laid the foundation for our understanding of the band structure, point defects, and impurities of the material. We will continue our studies on the fundamental properties of gallium oxide, including doping, electron transport, thermal properties, and surfaces to gain a comprehensive understanding of this material.
I'm Chris Van der Waals. I hope you've enjoyed these vignettes about our research and we'll be happy to personally discuss any of these topics with you.